Hello everyone. Today we will discuss or we will complete our discussion on the Landauer model of transport in the context of MOSFETs, and then we will discuss some of the ideas related to the ballistic MOSFET particularly. Okay. So this is going to be an interesting discussion because how do we understand the IV characteristics in ballistic MOSFET, and how do we understand the saturation of IV characteristics in ballistic MOSFET? That is what we hope we will possibly understand during the course of this discussion, maybe in this class or in the coming class. Okay. So let me quickly review what we have seen so far. So in the Landauer formalism of transport, this is the current equation that we start with, and this equation was although derived for a two terminal device in our discussion, but this is equally applicable to the MOSFET device as well. And while we try to use this equation in the context of MOSFET, we will generally compare this to our conventional equation, this equation, and that way we can try to understand what is the velocity, average velocity with which the charge carriers are moving in the MOSFET, and what is the total charge in the MOSFET. This charge can also be calculated from our expression of charge, which looks like this in the steady state. So this is the charge in the steady state. It also comes from the general model of the transport, and this is generally can be written as dE times F1 plus F2 by 2 dE. So this is the total number of charge carriers at steady state in the channel. Q is the charge. In this case it will be negative, so we will use a negative sign while doing the discussion of the charge in the MOSFET. So as you know that that in our Landauer approach of transport, generally this you might recall from our previous discussion as well, that generally we try to understand the IV characteristics for small biases or in the linear regime, because small bias is in the linear regime of the IV characteristics of the MOSFET, and for large biases, which is the saturation regime. And at extremely low temperatures, this entire analysis becomes very easy. It becomes pretty easy to understand, and at higher temperatures, since the Fermi window, the idea of Fermi window or this term F1 minus F2, this becomes quite complex, and that is why we need to use the Fermi Dirac integrals. In order to account for the scattering in the channel, we use a transmission coefficient parameter, which is TE parameter, and this TE parameter from our derivation, this turns out to be lambda by L, where lambda is the mean free path, and more precisely it is TE is lambda E divided by lambda E plus L. And in our previous class we discussed that the unidirectional thermal velocity is the velocity which is defined as the velocity of electrons going from the source side to the drain side, and it is averaged over angle and averaged over various energy states, and this is what is the expression of the double average. And unidirectional thermal velocity is generally defined as the velocity in the case of when we consider the non-degenerate semiconductor, and this is the expression of the unidirectional thermal velocity, because this Fermi Dirac integral in the numerator and in the denominator, they will cancel out each other when we are considering a non-degenerate semiconductor. Okay. So, this is what we have, and this is also the situation below threshold in the MOSFET, because below threshold not much charge is there in the channel, which means that still the conditions like non-degenerate semiconductor conditions are maintained. And there is one interesting aspect here, which is that for the electrons sitting in the conduction band, in the case of non-degenerate semiconductor, the electrons sitting in the conduction band will look something like this. We will have electrons here. Okay. And for a non-degenerate semiconductor, this EF, the Fermi level is significantly far away from the bottom of the conduction band. Okay. And the energy of electrons, which is just above the bottom of the conduction band, is larger than EF, and it is quite significantly larger than EF, or it is many kT times, or what we can write is E is EF plus kT times C, where C is a good number. C is maybe 9, 10 or maybe more than that. So, in that case, this Fermi-Dirac distribution function, this exponential term becomes large, and as compared to 1, and it can be approximated by the Maxwell distribution function. So, this Fermi-Dirac distribution function can be approximated by the Maxwell distribution function in the case of non-degenerate semiconductors, which is actually the case in most of the practical devices, and that is why these Fermi-Dirac integrals can be approximated by exponentials, and that is why we can cancel out the term in the numerator and the denominator, and that is why this thermal velocity is defined as unidirectional thermal velocity is just defined as this thing without the Fermi-Dirac integrals, because this is the velocity at equilibrium, which means we are assuming that the below threshold conditions are prevailing, and below threshold conditions are the conditions which are quite similar to the non-degenerate case conditions. However, when current is flowing through the device, in that case we cannot make this approximation, we cannot approximate the Fermi-Dirac integrals by the exponentials, and we need to explicitly solve for them. Okay. In some cases, although, in order to have a better understanding, we try to actually approximate the Fermi-Dirac integrals by the exponentials. So I hope this idea of the unidirectional thermal velocity is clear, and a related idea is the idea of the injection velocity, ballistic injection velocity, that will become apparent in the discussion of the ballistic MOSFET. Before going to the topic of the ballistic MOSFET, let us quickly revise the idea of modes in the Landauer transport model. In the modes are defined as the conduction pathways, and this we have I guess repeated many times by now, that modes are defined as the conduction pathways, and the reason is that when electrons travel through the channel, they travel through the energy states, but because of the finite lifetime of electrons in these energy states are broadened, and that results in a broadened pathway in the channel, which is different from the energy states, or this parameter m, which is the modes, it becomes different from the density of states, and that is precisely the reason that we need to introduce a new parameter in the general model of transport, which is known as the modes in the channel. Okay. So, for a 2D channel, the modes are defined as ME is equal to h by 4 average velocity in x direction times the density of states of the device for a 2D channel. And for a 2D channel, we can do this calculation explicitly. The density of states is given by m star by pi h bar square, and the average velocity, this average is taken over the angles, this will be given by 2 by pi times VE, and if we put these expressions together, then this is what we obtain. So, the modes in a 2D channel is square root of 2 m star E minus EC plus epsilon 1 divided by pi h bar, where this epsilon 1 is the energy or the ground state energy of the first subband. So, actually a 2D material is practically a quasi 3D material, because there is a finite thickness of the material. So, there is a confinement in the third direction as well, and because of that subbands arise in a 2D material, and that results in this. So, that modifies the ground state of the electrons, and so that is why we need to account for this parameter epsilon 1 as well. So, this is the parameter that also appears in the current expression, and while explicitly calculating the current in the channel, we will use this expression actually. And this is the difference between the density of states and the modes, as is clear. They are quite different from each other. In a 2D material, the density of state is independent of the energy of the state. It is the same for all possible energies in the conduction band, but the number of modes, as you can see, it is low for energies close to the bottom of the conduction band, and it increases as we go far away from the bottom of the conduction band, which means that very few conduction pathways are there at the bottom of the conduction band in a 2D channel. Although, so these two ideas are related, but physically and intuitively they have quite different implications. So, this is just to quickly review the idea of modes. So, we will use this idea of modes in while calculating the current in the MOSFET, particularly in ballistic MOSFET, or even in a diffusive MOSFET using the Landauer model of transport. So, once we have this idea of modes with us, we can calculate the conductance of the channel as well, conductance of the device as well. And if you recall our discussion, the conductance expression can very cleanly be calculated for near equilibrium transport, which means near equilibrium means that the applied voltage is not so high. So, it is a small applied, so at small applied voltages the conductance is given by 2q square by h from the current expression Te Me minus del F by del E integrated over energy. And at T equal to 0 Kelvin, this expression assumes a very clean form, because this derivative here, this changes to a delta function, and so this integral vanishes, and which means that at T equal to 0 Kelvin, this turns out to be 2q square by h Tef. This is a delta function at the Fermi energy. So, it becomes transmission coefficient at energy Ef times the modes at energy Ef. Okay. And if we make this calculation explicitly, and for a ballistic conductor Te is 1 and this 2q square by h is 1 by 12.9 kilo ohms. So, the conductance is equal to the number of modes divided by 12.9 kilo ohms, which means that the conductance of a single mode is 1 by 12.9 kilo ohms, or this unit of the conductance is the inverse of the ohm. This ohm comes in the numerator. When the temperature is not 0 Kelvin at room temperature, in practical situations what happens is that this current expression then takes the integral in the current expression is converted to the Fermi-Dirac integral. So, this idea of number of modes and the idea of conductance is, I hope clear. Now, now we come to this an important idea, which is the carrier densities or number of charge carriers in the channel in the Landauer transport model. And if you recall, in an arbitrary semiconductor, the number of electrons or the number of charge carriers in the conduction band is given by this integral from EC to infinity dE number of electrons per unit area will be, the charge density will be, and this is actually the d 2d E parameter. In a device, in a two terminal device and also in a MOSFET, the charge carriers or the charge carrier density will be given by this parameter Fs plus d2de Fde 1 by 2 dE. So, this will be the carrier density in the channel, and if you remember our general form of the current, this is the general form of the current in the MOSFET. So, this charge in the channel, the charge density in the channel is actually obtained by this expression here. Okay. So, please keep this in mind, this is an important parameter and it depends on the electrostatics of the MOSFET that we will study in coming discussions, but a straightforward way to calculate the carrier density, the charge density, the number of electrons per unit area in the channel is by using this expression. Okay. So, in order to calculate this expression, let us first see how this expression actually looks like. This is the expression for a general semiconductor when there is it is in contact with a or when it has a Fermi function Fe and density of states d2dE. So, in that case, in a 2D case, this is how it looks like. d2dE is m star divided by pi h bar square and the Fermi function is 1 by 1 plus exponential E minus Ef by kT. Now, this integral is again transformed into a Fermi-Dirac integral by replacing the variables like this: E minus Ec, eta is defined as E minus Ec by kT and eta f is defined as Ef minus Ec by kT. So, which means that E minus Ef by kT is actually eta minus eta f, and this is the exponent in the Fermi function. So, this exponent E minus Ef by kT can be replaced by eta minus eta f, and this dE can be replaced by kT times d eta. So, finally, this carrier density Ns turns out to be m star kT divided by pi h bar square, limits transform from 0 to infinity d eta by 1 plus exponential eta minus eta f. And if you remember the Fermi-Dirac the form of the Fermi-Dirac integral, this is the Fermi-Dirac integral of order 0. So, this becomes m star kT pi h bar square Fermi-Dirac integral of order 0. So, this is the number of electrons in the channel per unit area, this is the density of electrons in the channel at a finite temperature. Now, by using or by having a generalization of this expression, we can calculate the electrons in the MOSFET as well, or the carrier density, charge density in the MOSFET as well, using this equation and this equation. And this is, again, please remember that this is an important parameter, because this tells us about how much charge is there in the channel while the MOSFET is conducting. Okay. So, generally this parameter m star kT by pi h bar square, m star kT by pi h bar square is defined as N2D, where N2D is the modified density of electrons. So, this carrier density becomes capital N2D times Fermi-Dirac integral of order 0. Okay. Now, it gives us an expression for the conductance as well. So, in a device, the carrier density is defined as this, which is essentially this. So, this means, just to quickly review what it means, this means that the source contact, the left hand side contact, is trying to fill the channel up to the source Fermi level, and the drain contact is trying to fill the channel up to the drain Fermi level. And in steady state, the channel can be assumed to be filled up to the halfway of the two Fermi levels. So, if, for example, if the source Fermi level is here, EFS is here, the drain Fermi level is here, it can be assumed that in steady state the channel Fermi function will be in the midway of the two Fermi levels, or the channel Fermi function can be assumed to be the average of the source and the drain Fermi functions. So, this f of the channel can be assumed to be the Fs plus Fd by 2. So, this calculation we have already done, because this d2de Fe by 2 is essentially N2d times Fermi-Dirac integral of order 0. So, this first term, the carrier density in the channel is N2d 1 by 2 N2d, because this 1 by 2 will come out, Fermi-Dirac integral of order 0 eta f, where eta f, please remember that it should be actually eta fs plus 1 by 2 N2d Fermi-Dirac integral of order 0 eta f d, because now this parameter eta f will be different for the source contact as compared to the drain contact, where eta f can be defined to be EFS, eta fs can be defined as eta EFS minus, so this eta fs can be defined as EFS minus EC by kT, and eta fd is defined as EFD minus EC by kT, and which ultimately gives us, and please remember that EFS minus EFD is Q times the applied voltage QV. So, which means that eta Fs minus eta Fd is QV times kT, or eta Fd is essentially eta Fs minus QV by kT. So, this eta Fd can be replaced by, so if we assume that eta Fs is eta F, So, this eta FD can be assumed to be eta F minus QV by KT. So, that is what it finally becomes. This becomes N2D Fermi-Dirac integral of order 0 eta F minus N2D plus Fermi-Dirac integral of order 0 eta F minus QV by KT. So, this is the steady state charge density in the device, in the MOSFET, according to the Landauer's formalism. And similarly, this conductance can also be calculated in this way. Okay. So, we have already seen the calculation of the conductance. This is quite a general, this is just a generalization of the Landauer model of transport that we discussed for a 2-terminal device to the MOSFET device. So, I would recommend all of you to do this calculation on your own. We have already done this. So, this will be a good exercise on your part. So, this essentially concludes our discussion of the main points of the Landauer model of transport in MOSFETs. So, we are now ready to understand the electrical characteristics of the ballistic MOSFET, and just to quickly review, the ballistic MOSFET cannot be understood in terms of the conventional conduction theory of electrons, which is based on the Drude's model. So, that is why we need this Landauer model of transport, and since we have discussed the main points of this, this new transport model, we are now ready to understand the ballistic MOSFET. So, in a ballistic MOSFET, the first thing that comes to our mind is that there is a left contact, source contact, there is a channel, there is a right contact in the device, there would be a third contact as well, which is also known as the gate contact or the control terminal. So, in a ballistic MOSFET, the electron starts from the left contact and directly goes to the right contact without any collision in the channel. So, it travels without collisions, which means that the transmission coefficient is 1. There is no collision, no scattering in the channel. So, the transmission factor is 1. So, in all the expressions that we have discussed so far in the Landauer model of transport, we need to put TE to be equal to 1 while we are dealing with a ballistic MOSFET. And there are many interesting ideas in the ballistic MOSFET. So, since there is no collision in the channel, the question is where is the resistance coming from, and this question we have addressed in detail. This resistance is coming from the contact, source contact, and the or from the interface between a bulk contact and a ballistic channel. So, the energy or the resistance is at the interface of the channel and the contact. The energy is dissipated in the channel, dissipated in the contact, not in the channel. So, all these things are all these ideas must be clear, because there might be a false notion that in ballistic MOSFETs the resistance will be 0. That is not the case. The resistance is there, and that is there because of the interface between the source and the channel and the drain and the channel. So, the current expression is, by putting TE is equal to 0 in Landauer formalism, the current expression becomes 2q by h ME modes times Fs minus Fd times dE. This is the drain current in a ballistic MOSFET. So, in the linear regime, when the applied voltage is very less, in that case the source Fermi function is very close to the drain Fermi function, and in that case this Fs minus Fd can be approximated by minus del F by del E times Q times V. So, the current in the linear regime actually becomes 2Q square by H ME times minus del F by del E times V times dE. And from here we can define the conductance of the MOSFET, which is 2Q square by H integration of ME times minus del F by del E into dE. And in the saturation regime, which is when a high voltage has been applied on the drain terminal, in that case the source Fermi function or the source Fermi level is well above the drain Fermi level, and in that case this difference between the source and the drain Fermi functions can be approximated by the just the source Fermi function, and it means that in saturation the drain current in the MOSFET is 2Q by H integration of ME times Fs E times dE. Okay, so these are the equations to start with while trying to understand a ballistic MOSFET. So, now the question is, how does the transport happen in a ballistic MOSFET? So, that is the first question that we will ask here. How does electron travel through this barrier in the MOSFET? And I will first let you think about this, and then in the next class we will start with this discussion, how the electron is essentially transported in a ballistic MOSFET, first intuitively and second mathematically. And then we come across an interesting fact that the current in ballistic MOSFET also saturates, even though there is no velocity saturation because of the scattering, and there is no pinch off, so called pinch off according to the conventional theory, but still there is a saturation, and there is a different reason for the saturation that we will see here. Okay, so please think about the electron movement across the barrier in a ballistic MOSFET, and we will start from this point in the next class. Thank you for your attention. See you in the next class.